So quantum gate U rotates a qubit, usually into a superposition. Of state 0 and state 1. The way that we can take U, take any quantum gate U, and put it into a matrix form is via this matrix notation. So we'll take the resulting amplitudes for the effects of U on 0 and the effects of U on 1 and pop them into this form here with our column vectors all come together to form a matrix. And now we can use this matrix representation to do things via linear algebra, which kind of simplifies the whole process. So let's say now we're applying this to state 0. Well, we know 0 is 1, 0 in this form. So, sorry, we've got 0, 0, and our matrix. And this results in A, B. And vice versa for due to this. Sorry. So we've got, for example, for 0, we'll take this and assess C and B times 1 plus D times 0, which leads us to AB. You can also act on superpositions, alpha and beta. So that's a terrible psi, but psi, alpha 0, and beta state 1. So the effects of psi are going to be our U matrix times the column vector representation here. As we can see here, it follows the exact same format here, so we wind up with A alpha plus beta times C and B alpha plus D times beta. These will be obviously two scalars representing the new amplitudes of our superposition after the U gate is operated there. So also, as we discussed yesterday, matrix gates, U gates, pardon me, let's call them U gates, are valid if they maintain normalization of the superposition. That is that the norm squares of alpha and beta have to equal 1, as these are probabilities. Once we take the norm square, this gives us our probabilities. And so we know that these two scalars, if we take the norm square of these two scalars, they should sum to 1. So let's scroll down. Let's do a just to solidify this. Let's do 3.12. So we have u of 0 is equivalent to 1 over square root of 2, 1i, and u square with u state 1 is 1 over square root of 2, negative I, 1. So how do we assess this as a matrix? Well, we know we've got these two column vectors. Let's go ahead and just combine them into our matrices. We could either distribute the 1 square root of 2 or just leave it out because it's shared there. So we have 1 minus I and minus I 1. What is u of alpha and beta? So again, we have some arbitrary state psi that is alpha's state 0 and beta state 1. In column vector form, we have alpha, beta. Now we're going to assess this on to here. So we have 1 over square root of 2 alpha minus beta I, and alpha, or pardon me, negative alpha I plus beta with this scaling factor here. We could distribute this through, but I'll just leave it out for right now. So from your answer to B, is U a valid quantum gate? So that depends if this sums to 1. So we know that squared plus beta squared is equal to 1. We need to see that this holds. So let's take this through. So 1 square root of 2 alpha minus beta I sorry. For simplicity's sake, let's just do this. We'll do it over square root of 2. So alpha minus beta imaginary I plus minus alpha I plus beta. So we want to see if the norm squares of these are going to wind up summing to 1. So we know that when we take the norm square, we are multiplying something by its complex conjugate. So that's going to mean that alpha minus beta I is going to be multiplied by alpha plus beta I over 2. And similarly here, we'll have, I'll just switch this around for easy reading here. So we'll have beta minus alpha I multiplied by beta plus alpha. That's alpha. Looks like an 8, I know, but trust me. Alpha I over 2. So now we can simplify here. Alpha squared. These middle terms cancel out, so we'll be left with so the minus beta alpha I and plus beta alpha I will cancel each other out. So we'll be left with minus beta squared I squared, which gives us plus beta squared because I equates to negative, I squared is negative 1 multiplied by the negative 1 there gives us beta squared over 2 plus, and similarly here we'll wind up with beta squared plus alpha squared over 2. Now we know that beta squared plus alpha squared plus beta squared is 1. So we can either take it algebraically to the conclusion, or we can understand that this is 1/2 and this is 1/2. So 1/2 plus 1/2 is 1. Or if we just want to see how it breaks down algebraically, we have 2 alpha squared plus 2 beta squared over 2. Bam. Take this out, and we're left with alpha squared plus beta squared, which is the same thing. So these new amplitudes maintain normalization. So U is therefore a valid quantum gate. All right, perfect. So 3.13, we're gotcha. Perfect. This is also available for free as a PDF online if you guys need it on your personal devices. You just Wong quantum computing, and I think it's the first result on Google. All right, so now we understand how a U-gate, how a matrix works on a superposition. It's simply going to interact with the amplitudes in their column vector format, and we'll just use matrix operations to work through that. Now we'll actually begin to see some of the common gates in their matrix form. So we've got our identity gate, which simply maintains whatever state that it's applied to. So 0 is still 0 after an application of identity gate. State 1 is still state 1 after the application of the identity gate, and the matrix representation is 0, 1, 0, 0, 1. We can see that act out here just as a quick linear algebraic proof here. So we have something that's in state 0, which is column vector state 1. The multiplication of I applied to this is going to be 1, 0, 0, 1 applied to the column vector 1, 0. This leads us to 1 times 1 plus 0 times 0 times 1 times 0 plus, or pardon me, yeah, 1 times 0 plus 0 times 1, which gives us 1 and 0. It preserves the state. Similarly here, we'll get into the poly X, the NOT gate, poly X, the NOT gate, negation gate is the classical analog there. So the X gate is going to flip whatever state into the opposite state. As we saw yesterday, the X gate operates by flipping the amplitudes. So if we have alpha state 0 plus beta state 1, and we're going to apply an X gate, the resulting, what results to the superposition after we apply the X gate is that these switch places, and we wind up with beta state 0 plus alpha state 1. So in the classic analog sense, where a bit is never in superposition, it's either 0 or 1, we could say, if we wanted to put this in the example of a superposition to see how it would work, we would say, if it's in state 0, if a classical bit is 0, then it's, the amplitude for state 0 is 1, and then the amplitude for state 0 or state 1 is 0. And then, well, the application of an X gate is going to flip this bit to 1. So it'll just flip these here. So now the amplitude, the probability of being 1 is now 100, and the probability of being 0 is now 0. And the matrix form for that is 0, 1, 1, 0. If you look at it that way, it's the I gate sort of transposed almost. All right, so that's the X gate. The Y gate, as we discussed yesterday, the poly Y gate assesses a 180-degree rotation of the qubit position around the y-axis, and it affects state 0 by putting it into I state 1 and state 1 into negative I, applying negative I to the amplitudes rather, and flipping the state to 1. Matrix form of 0 minus I, 0. And we'll work through using these matrix forms in the example problems coming up. So the poly Z gate, which assesses a 180-degree rotation around the Z axis. State 0 remains state 0, and it negates the amplitude for state 1. Matrix format of 1, 0, 0, minus 1. Our other more niche gates here. So the S gate is the square root of Z. It assesses a 90-degree rotation around the Z-axis. It does the same thing with 0, where it maintains state 0, leaves its amplitude the same, and for 1, we wind up with multiplying the amplitude for 1 by imaginary I. Very similar to its father, the Z gate. We have 1, 0, 0, and then I instead of negative 1. So, looking back to what we were looking at with how we even write things in, so we have our amplitudes and we assess a gate, and then they funnel through the matrix operation to, where are we? Yeah. So, let's say we have this A, B, C, and D, and we're applying it to a superposition, or this is a single state, but let's say we're applying it to a superposition. Then essentially these are our amplitudes. They are going to get multiplied in, and we'll get 2 scalar results, which will represent the new amplitudes once that gate is applied. And so we'll see that when we get through these specific problems coming up. So S. This is also known as the phase S. In terms of the T gate, this is another offspring of the Z gate. This assesses a 45-degree rotation around the Z-axis. Around, oh, this is gibberish, around Z. So again, state 0 is left untouched. The amplitudes are not affected. and 1, our amplitude is going to be affected by e raised to the power of I pi over 4, state 1. We're rotating our amplitude around the circle, the surface of the Bloch sphere by 45 degrees. So our phase, or pardon me, our amplitude for 1 will be impacted by this phase factor here. The similar to its cousins, 1, 0, 0, and e raised to the power of I pi minus 4. Yeah, so Hadamard H, that one is the GOAT. Hadamard. It splits 0 and 1 into equal superpositions. So 1 square root of 2, 1 over square root of 2, pardon me, plus equal parts state 0 and state 1. Same thing when we apply it to 1. We wind up with a superposition of 0 and 1. However, you'll notice that when we apply to a state 1, we are negating the amplitude for state 1. That's as part of the transformation. So here, amplitude for state 1 is maintained, but we have this this global scaling factor. But with the Hadamard applied to state 1, we are applying a -1 multiplier to the amplitude for state 1. Matrix form, 1 over square root of 2, 1, 1, 1, -1. Perfect. So let's see, let's use some of these in action with some example problems. So this is just a breakdown of what I worked through earlier, showing how the identity matrix operates. Excuse me. All right. Well, we'll look at sequences, and then we can. I'm sure there are some. Yeah, there are some practice problems down here, where we can actually use our new matrix representations. All right, so sequential sequences go from right to left. So if we are applying this to a state, this is our first one, this is our second one, third one, our fourth one, and each next part is going to operate on what results from the gate operation before them. So the T gate is going to operate on the Hadamard effect on this guy, and then our T gate does its thing, and then the S gate is assessed on the result of this, and so it ripples down. So just excuse me. So we will work through this example. So we've got 0 as our starting state. We know that when we apply a Hadamard gate to 0, we wind up with an equal superposition of state 0 and state 1. Now we will apply the T gate to this superposition. The T gate applies a 45-degree rotation around the z-axis, matrix form of 1, 0, 0, e pi to the 4. And since we're keeping this in matrix and vector notation, so we can do actual matrix operations, the Hadamard result here is 1 over 2, 1, 1, or forget that little line there. So we'll just keep pushing this 1 over square root of 2 forward. We could combine it, but I like to watch the ripple action downward to see how everything comes together. So now we have 1 and 1. Once again, we'll apply these new amplitudes, the gate with this gate. So we'll wind up with 1 square root of 2 over square root of 2, 1 times 1 plus 0 times 1, 1 times 0 plus 1 times e raised to the I pi over 4, which gives us 1 over square root of 2, 1 over e raised to I pi over 4. So now this will get operated upon by our S gate. So S gate is 1, 0, 0, I. We'll come in here, we'll pull this 1 square root of 2 out. Just let that trickle on down. 1 e raised to the I pi over 4. Similar as the step before. 1 times 1 plus 0 times e I pi to the 4, or pardon me, plus 1 square root of 2 there, and 1 times 0 plus I times e raised to the power of I pi over 4. So we are going to move that. It looks like in the next one they're going to move that into the term there. So we wind up with 1 ei 3 pi over 4, which I'm not certain how they got there. So I have a 4. So we'll look into that. All right. I know my E rules, and I sometimes have to revisit those. Finally, we'll apply the H gate to these amplitudes. We know that the H gate is 1 over square root of 2, 1, 1, 1, negative 1. Pi over 4. Finally, we'll see that these will come together and form 1/2. And we'll just follow through the exact same way that we've been doing things before here. So 1 times 1 plus 1 times e I 3 pi over 4, and 1 times 1 minus 1 times e I 3 pi over 4. So our final result for our superposition is going to be 1 plus ei 3 pi over 4 and 1 minus e raised to the I 3 pi over 4. And these are amplitudes of our new superposition. In other words, we could write this as 1/2 1 plus e raised to the I 3 pi over 4, state 0, plus 1 minus e I 3 pi over 4, state 1. Perfect. So we start from the right, and we just apply those matrix vector multiplications until we reach the left side. We're not using Mathematica, thank God. Okay, we can work through, let's work through 3.15 as another example. This time using a custom U-gate with some effects with some values that we haven't used before. So U is equal to 2. Oh, I think I made this mistake when I first did this problem. I wrote square root of 2 minus I instead of square root of 2 minus I over 2 minus 1/2 and 1/2 square root of 2 plus I over 2. So we have HTU being assessed on position state 0. Excuse me. So what we'll wind up with, we'll start here. So we've got 0, column vector form 1, 0. We will multiply this, we'll do a matrix vector multiplication. So we know that that gives us, that the result of U on 0 is going to give us 1 times square root of 2 minus I over 2 plus 1/2 times 0 and minus 1/2 times 1 plus 0 times square root of 2 plus I over 2. We wind up with square root of 2 minus I over 2 over minus 1/2. So we're going to continue forward with our T-gate. So 2 and minus 1/2. Our T-gate is in the form 1, 0, 0, E I pi over 4. We'll bring that in here. Multiplying our amplitudes times our gate, we wind up with square root of 2 minus I over 2 and minus E I pi to the pi divided by 4 over 2. Okay, and once again, now we'll apply the final gate, which is the H gate. To this state. 1 over square root of 2, 1, and times our amplitudes, above, so our amplitudes here winds up with 1 over square root of 2, 1 times square root of 2 minus I. Just verify that I didn't. Okay, perfect. Si over 2 plus 1 times negative EI pi divided by 4 over 2 and 1 times 2 minus I over 2, square root of 2 minus I over 2 plus negative 1 times negative EI pi over 4 over 2. Simplify things, group the like terms, etc. We wind up with 1 over square root of 2 square root of 2 minus I plus, or pardon me, root of 2 minus e I pi over 4 over 2, and square root of 2 minus I plus, these are going to turn to pluses here, over 4 divided by 2. We could probably even take this a step further if we wanted to get rid of these the fractions here. We could pull out a 1/2 from each of these, and so we could say 1 over 2 square roots of 2, just with our numerators as the amplitudes. But that is that gate sequence applied to the state 0. Just going to double check that I didn't mess anything up here. 3.15. Perfect. Yep, the answer key is precise. All right. So there are certain circuit sequences that are equivalent. We'll take a look at some of these here, some of the circuit identities. So this was on the first problem set, where they asked you to show that whether it was true or false that something was equivalent to something else. We can look at that we'll look at the first problem set in the second half of the session. Pardon me. So HXH equals 1 Z gate. We can prove this algebraically by showing the linear algebra form. But essentially, once we take these various matrices and multiply them through, we wind up with the exact same form of Z. So this is equivalent to 1, 0, 0, negative 1, as is this. So these two forms, applying an H, an X, and an H, you're basically just applying a Z gate. All right, let's do 3.16. Kind of a similar example, looking at an identity. So XY, to prove that XY equals imaginary I times Z. So essentially, these have the same impacts. So we'll show this first, showing that XY on state 0 is the same thing as applying I Z to 0. So the Y gate applied to 0 is all right, perfect. So Y form, we got 1, 0, and the Y form is one second. Ah, 0 minus I 0. This is definitely something that's going on the note sheet for the exam. It's hard to keep track sometimes of every single matrix form. So we've got our transformation here, and then if we're applying Z 2, 0, well, we know that it's 1, 0, 0, negative 1 to this 1, 0. So I'll work out the right side first. So we wind up with 0 times 1, 0 times 1 plus negative 1 times 0. We wind up with 1 and 0. Remember, the z-gate does not affect 0 at all. So bringing in our I, that means we will wind up with I0 when that is applied. So let's see if this can equate to I0 in column vector form. So 1 times 0 plus 0 times negative I, and I times 1 plus 0 times 0 gives us a result of 0I as a result of applying y to our 0 state. Now we're going to apply x. X just flips everything, right? So we've got the format here, which is 0, 1, 1, 0. Our state 0 and state 1 column vectors just inverted, right? So with 1 in the place of 0 and 0 in the place of 1, times our 0I. Following this through, we have 0 times 0 plus 1 times I, 0 times 1 plus 0 times I. And we discover that these are indeed equivalent. Simplifying here, we've got 0 plus I, and 0 plus 0, 0. So the x and y gate applied to state 0 is the same as applying a z gate to 0 and then multiplying by I. And we can also simply show that the multiplication of the x and y matrices equals the I and z. So we've got our two, we've got 0, 1, 1, 0 multiplied by 0, negative I, 0. Let's see if I bundle that. Yes, perfect. 0 is going to be equivalent to I times I times 1, 0, 0, negative 1. We've got things operating this way. Zero times I, or 0 times 0 plus I times 1 minus I times 1 no, I bungled this. There we go. We'll say that these two are equivalent. We proved that in part A. We'll see what time is it. Okay, we're about 50 minutes in. We've got unitary state, we've got unitary reversibility, and outer products left in this chapter. Try to get this done in the next 15 to 20 minutes. So we can take a look at chapter 4 and get set up for a good look at the knowledge checks and problem set 1 for the second half. So We also know that valid quantum gates are unitary. So what does that mean? So that means that for some quantum gate U, when we take the complex conjugate, or pardon me, the conjugate transpose U, and I just draw this like a tie. I'm gonna say I don't have the artistic skills here, so, or it looks like a hot pepper right now, but so if we take U and its complex conjugate, or its conjugate transpose, pardon me, and we multiply them, they will equal an identity matrix. And vice versa. This could be U dagger multiplied by these will both equate, will become the identity matrix. This we can work through this. Are you guys interested in working through the actual proof of this, or are we good with that? All right, we'll move on from that. So that's also why we use U. U for unitary. All right, so let's take a look and see if, let's just take a look at 3.17 just to show kind of how to explore this unitariness, shall we say. So U is equivalent to 1 over square root of 2, 1 I negative 1. Sort of a mixture of a weird Z gate and some other stuff going on there. But so if we want to know if it's a valid quantum gate, we need to make sure that it's unitary. So we need to calculate U dagger thing. Weird stick person. And we need to determine that U dagger is equal to the identity matrix. So let's check that out. So we want to take the U dagger is going to be equal to the conjugate transpose. So first we'll transpose it. So our imaginary components will switch places. And then we also negate any imaginary components. Bam. Square root of 2. Now we'll multiply these together. So we wind up with 1 over square root of 2 times 1 over square root of 2. We'll pull those out together. And 1I negative 1, 1 minus I minus 1. This becomes 1/2. And we evaluate these into our form here. So what we want is a 2 by 2 identity matrix, like this, with ones on the diagonal. And what we get when we bring this in is just that. Or pardon me, it's 2 here. Bringing in our 1/2, we then get 1, 0, 0, 1. So the 2 seconds, sorry. This is indeed a valid quantum gate. So we can define, U can be any arbitrary quantum gate as long as it doesn't affect normalization, and it's also unitary. So it times its conjugate transpose has to equal the identity. So valid quantum gate U. All right, reversibility. So this plays into, when we were talking about yesterday about in classical computing how we've got reversible circuits, reversible gates. So not all classical gates are reversible, but every quantum gate has to be reversible. So in matrix terms, matrix M is reversible or invertible if we can find the inverse of it, such that when we multiply M times its own inverse, we get the identity matrix, or these can be switched, it's equivalent. So similar to the unitary condition, talking about it in matrix terms, it's reversible if we can find this inverted form here that gives us the identity when we multiply it by our normal matrix, our original matrix. Well, we already know what M minus 1 equals, right? We just looked at this. So M minus 1 for any quantum gate, and the arbitrary quantum gate U, will just be the conjugate transpose U dagger. And these just keep getting worse. Okay. Also, any quantum gate that we apply, so if we apply quantum gate U to a state psi, we can undo it simply by multiplying the result by the conjugate transpose. So obviously, since U is arbitrary, right? U technically, it can represent any gate, and for notation. So let's say you apply a Hadamard gate to psi, and now you want to undo that Hadamard operation. You would just simply apply the conjugate transpose of the Hadamard gate. Bam, now you're back to psi. In this example here, in 3.19, I'm not sure if I worked through, let me see if I worked through this one on paper. I did not. But, we would come in here, we would take U, we would transpose it, and then we would flip the signs of all of our complex numbers. And then, for example, it says here, what is U dagger U assessed on psi? Well, we know that those two cancel each other out. So the result is simply the original state psi with this original superposition. Just as an example, let's just look at this and look at getting the inverse, getting U inverse, also known as U dagger, or the conjugate transpose, real quick. So, because this looked like it was a 2x4 at first, but it's actually a 2x2. So we're going to take the transpose. So the transpose will flip it along this diagonal, and then we'll flip all the signs of our complex numbers. So we've got 1 plus square root, we'll do the transposition first. So we've got 1 plus square root of 3 over 2 square roots of 2 plus I1 minus square root of 3 over 2 square roots of 6. These two are going to switch places because we're taking the transpose. So we'll wind up with 1 minus square root of 3, 2 square roots of 6, plus I 1 minus 3, over 2 square roots of 6. Similarly, this column, or pardon me, this column becomes a row. We wind up with, I might run out of room. Okay, 1 plus square root of 3 over 2 square roots of 2 plus I minus I multiplied by minus 1 plus square root of 3 over 2 square roots of 6. And this guy right here is moving up here. So minus 1 plus square root of 3 over 2 square roots of 6 plus I 1 minus square root of 3. Oh, Christ. Let's just start over on this little section. I 1 minus square root of 3 over 2 square roots of 6. So that's the transposition, right? We flipped our rows have become columns, and our columns have become rows. Now we need to take the conjugate part, where we need to assess the negation of all of our complex parts. So what we wind up with here is minus I. Let me just erase these signs real quick. Oh. So minus I minus, oh, that's not even part of the show. Minus and minus. So we flip all the signs. And we have just taken U. We found the inverse of this quantum gate, U inverse, also known as U dagger, the U conjugate transpose. And it is such that when we multiply these two together, we get an identity matrix. So identity times psi just gives us psi. Okay, final topic in the linear algebra section, outer products. I'm actually going to grab a 5-minute break until, so what it's 7:04 Eastern. So at 7:10, I'm going to reconvene. We'll finish up this last section here and then dive into the multiple qubit stuff, which is really the bulk of the course. We didn't do a ton of stuff with single qubits, and we'll get to work with the quantum circuits, etc. So I will be back at 7:10 Eastern in about 5.5 minutes. All right, Space Cadets, let's get back in there. So, outer products. Final big things on the topic here. Excuse me. Outer products. So, as we discussed yesterday, when we have a ket representing state psi, let's say that's alpha T1, and we have another ket, we'll call this rho. It's this weird y thing. We can multiply them by actually, and so instead before we saw doing a bra and a ket. So doing it something like this. But we can also do it like this. We can multiply a ket times a bra, which gives us the outer product, which is equivalent to column vector alpha beta times the complex conjugate weird y thing star other thing. I don't know what these Greek letters are called. The result is we take each row of psi and multiply it by each column of rho. So we can evaluate this according to the example they have here as alpha y. We'll do it in the simpler form first. And alpha beta, not squiggly 8 thing, equals alpha beta and alpha and beta. So we can work through an example here to see how this works. Excuse me. So let's say that we have some gate operator U that assesses the outer product of state 1 and state 0 plus the outer product of state 0 and state 1. How does this affect this arbitrary state psi? All right, so applying that there, U applied to state psi gives us outer product 1 and 0 plus outer product of 0 and 1 multiplied by this superposition. Distributing things through, what we wind up with is alpha 1, and then we have this inner product of ket 0 of bra 0 and ket 0, which we know is just going to equate to 1 plus beta 0, or pardon me, beta of 1 and 0 and 1, which equates to 0. The inner product of, we discussed this yesterday, the inner product of state 0 and state 1, those are two basis states. So the inner product of any two basis states, of two states, if they do form a basis, will be 0, because they're orthogonal to each other. They're on opposite sides of the Bloch sphere in respect to each other. So plus, now let's bring this over, this part over. So alpha 0 plus 1, 0, which again 0, plus beta okay, I started doing this yesterday and I have no idea why. Okay, let's go back to the mouse and see if we can undo this. Yeah, these lines don't go away for some reason. So plus beta of 0 1 and 1, inner product of 1 and 1, which we know is equals 1. So getting everything if this will let me pan, it will not. Let me unplug this. Sorry, let me get my pencil pad restarted here. It's one of those bargain Amazon kind of electronic device things. Sometimes you get an absolute gem for $10. Sometimes you do not. So we wind up, after everything simplifies, with alpha 1 plus beta 1 plus beta 1 plus alpha 0 plus beta 0. Which equals, can I pan now, please? Okay, we'll just make this smaller. I'll have to start a fresh board after this. Is equal to alpha plus beta. I am completely spacing out on this. Sorry, we're multiplying times 0, so these guys are gone. So these guys are gone. sorry. A of 0 is gone. This is gone, and B of 0 remains. So our result is alpha of state 1 plus beta of state 0. We'll rewrite this for beta state 0 plus alpha state 1. And we've seen this before. So now it decides to start panning around. Okay. We've seen this before. So the X gate switches amplitudes. So this operation here, using outer products, actually has the same effect. So U equals the outer product of 1 and 0 added to the outer product of 0 and 1. And this actually just equals the same effect of an X gate, just switching the amplitudes between state 0 and 1. The matrix form here just shows exactly what we just worked through. So taking our column vectors, so we can break the outer product of 1 and 0 into 0, 1, 1, 0, added to the outer product of 1, 0, 0, 1. This results in 0, 0, 1, 0 plus 0, 1, 0, 0. Adding these two 2 by 2 matrices together, we get 0, 1, 1, 0, which is equal to the matrix form for the X gate. So we can prove this both by using this format, and we can also confirm it via the X gate using the matrix. Also, the outer product of, you can look at it the other way. So the outer product of rho and psi is just equivalent to psi outer product rho and the conjugate transpose of that outer product. They have a little proof here that that shows you the equivalency between those two. All right. Let's just really quick, let's just work through this. Okay. You can't even erase these lines. I have no idea what this is. All right, I'll just start a new whiteboard. These are all the ones that I had to start because of that weird bug. I should probably upgrade the hardware if I'm going to do this consistently. All right, so 3.4, or pardon me, 3.2, 3.20 rather. So we have I and we have minus. What is the outer product between these two? So we know that I is of the form we know that I has the form there you go. So I is equal to the superposition 1 over square root of 2 times state 0 plus I state 1. And the minus state is traditionally 1 over square root of 2 state 0 minus state 1. We'll put these into their matrix forms. So in the matrix form of I is 1 over square root of 2, or, pardon me, 1 over square root of 2, 1 I. And the vector form of this is going to be 1 over square root of 2, 1 and negative 1. So in order to take the outer product, we need to take the complex conjugate of the minus state. Double checking. Yes. So we're going to take the complex conjugate of the minus state, which is exactly the same. One over square root of 2. So we'll pull these out. And we'll just work through this just as the example they have here. So 1 over I times 1 and 1 over I times negative 1. So we get 1/2 1I negative 1 negative I. Now, the question is this a valid quantum gate? Well, we need to know if this is unitary. Well, okay, sorry. We need to know if these are unitary with regards to each other. So we'll call this result J, the J gate, or we'll just call this U. Let's use the actual terminology. So let's see if U, this result here, is actually unitary. So we'll take the conjugate transpose, pardon me. So we'll transpose this. So 1/2 1I minus 1 minus I times its complex conjugate, or pardon me, times its conjugate transpose. So rows become columns. And we're also going to flip the signs of all of our complex parts here. So these become positive. We wind up with 1/4 and let's solve for our 2 by 2 matrix here. So 1 plus I squared plus I squared 1 minus I seconds. I think I'm butchering this notation. Okay. Okay. All right, so we have 1 plus 1. So 1 times 1 plus -1 times -1. And we have I minus 1. Conversely, we have I plus I, and we have I plus I and I squared minus I. So I think I went astray somewhere, I'm not going to lie. Because this should give us 1/4 2I minus 1 I squared minus I, which is not an identity matrix. So either this is not an identity matrix, or either this is not a valid quantum gate, or I did something mathematically wrong. Let's just take a look at the answer for 3.20. Oh, I was indeed correct. It is once we multiply U times its conjugate transpose, there's this result that we get is valid, and it is not an identity matrix. Perfect. Completeness relation. So we have some orthonormal basis. So any two, sorry, let me erase this. So any two states that are orthonormal with regards to each other, so they have to be orthogonal. They have to be on opposite sides of the block sphere from each other. Essentially, if we take A's, let's say A is here on our block sphere, then if we draw a straight line from B, the inner product, the angle of this line is going to be 0. So they're exactly on the same plane. Opposite sides of block sphere. And they have to be normal. So that is that for an amplitude alpha and amplitudes alpha and beta, they have to be 1 when summed up when we take our norm squares. Whatever, that's an alpha, that's a beta. So if we have two basis states by which, and if something is a basis, then we can measure in it, right? So if we have our orthonormal basis, A and B, we can write this as, the whatever, the alpha, which is the, oh Lord, that's actually just an A, plus beta B, we'll call this psi. So some portion of it will be in state A and state B with their given norm squared probabilities. But we can actually substitute in these values for alpha. So alpha is the inner product of the state of A and state psi. We looked at this yesterday. Basically, if you don't know the amplitudes, you can discover them by doing the inner products with your measurement basis states, and it'll give you your amplitudes. And beta is equivalent to B, inner product with psi. So the inner products are just scalars, right? They're just numbers. Just some kind of float, right? Some kind of decimal value denoting okay. Right, let's just zoom out here. So instead of just, as it says here, instead of just multiplying them onto the vectors A and B, we can equivalently multiply them on the right. So again, if we have 2 times 3, where 3 is, for example, this, again, it wouldn't be, but let's say we have 2 times 0.5, and this is kind of equates to this, right? This inner product. Well, this is literally the same thing as saying 0.5 times 2. It's the commutative property. It doesn't matter which one is there. So we can equivalently say, instead of saying inner product of A and psi multiplied by A, we can actually put this here. And that has the effect of creating an outer product between these two, because this is just equivalent to this in notation, right? We usually just write it with one line for notation purposes, but essentially now we can break this down as, instead of A multiplied by the inner product of A and psi, we can now do an outer product of A with A multiplied by psi. Doing that with beta as well, we wind up with B. So we have the outer product of B with itself times psi, which can further be rewritten as the outer product of A with A plus the outer product of B with B multiplied by psi. So in order for that to be true, right, in order for this to be, actually, I apologize. This is important, right? So all of this times psi has to equal psi. Working back, we know that we put our inner products, we put our amplitudes in the form of inner products. Then we extracted outer products from that notation. Then we grouped the outer products. And this is equivalent to our original state, right? Our original state that we had up here. This guy. So we've just essentially taken this and we transformed it into this. So, what does that allow us to do? Well, it means that this portion, for these to be equivalent, the outer products of these basis vectors added together have to be an identity matrix, right? Because how else are we going to apply this to psi and then get psi? This is called the completeness relation. So basically, it means that we can express any qubit, or express the state of any qubit in terms of its basis. Which, again, we've discussed a lot of different bases, right? So we could have the arbitrary base A and B, like in this example, but it also essentially allows us to express the, it allows us to express in the z basis, right? The 0 and 1, or plus and minus. So we can take a look at, so all of these bases here are complete. That is, that we can express the qubit state using these bases instead of arbitrary amplitudes, right? Or not arbitrary, but instead of having some psi with, you know, alpha and beta, etc., we can use these outer products. So let's say we have the z basis. So we can rewrite this. We can rewrite psi as 0 plus 0 plus 1, the outer product of 0 times itself with itself, and the outer product of 1 with itself, psi. We could do some of these examples if you guys are interested. It's not really something I'm really concerned about. It's a cool property, but I haven't seen anything specifically using that. So we've got, unfortunately, we didn't make it as far as I wanted to. We've got 16 minutes until the switch over to problem sets and knowledge checks. Let's just dig in here. The chapter 4 is where things really get going. Honestly, the homeworks and stuff, the problem set, the labs, etc., really pick up here with multiple quantum bits. It's just, obviously those first few chapters are foundational to understanding what happens when we get here. Yeah, let's just move into multiple qubit states, so let's say, just a quick note on notation here. Let's say we have qubit A and qubit B that are both in state 0. We can write the states as 0, 0 together, right, with qubit A and qubit B, or rather for indexing, proper indexing, let's call these qubit 1 and qubit 2. So 1 and 2, they're both in state 0. This decomposes to this, right? But this is also equivalent to this, which is our tensor product. So with 2 qubits, the number of possibilities of superposition increase. It's 2 to the n, right? So let's say back when we had 1 qubit, we were seeing things like the Hadamard with 1 over square root of 2, state 0 and state 1. Half chance of being in state 0 being in state 1. Now, with 2 qubits, well, now we've got, let's say we have 2 qubits that have been, had Hadamard gates applied to them, right? So now we have 2 qubits, each that have a 1/2 chance of being in 0 or 1. And so now we have 4 different combinations. So the complete superposition for a 2 qubit system with these Hadamard examples, with these 2 qubit state examples, let's say this is Q1 and Q2, is 0, 0 with some amplitude. They use C's here, so C0 plus C1 0 1 plus C2 1 0, and then obviously when they're both 1. So however many qubits that we have 2 to the n, 2 to n, 2 to n, where n is the number of qubits. Provided that they're in some type of superposition, right? Depending on what gates, etc., have been applied, you could have 100% chance of being in 0, so it's just state 0, etc. We'll start to see that, and also in the case of entanglement, right? A certain state given is impossible, so it's just not included in the superposition. So this decimal representation, the binary string, not something I'm going to worry about going over, because this is pretty so all we need to know from this part is the little endian. So essentially when we're writing basis states, the first qubit is going to be on the right. So let's say we have a superposition of, or we have 3 qubits, like so. This is actually our first qubit. This is our second. This is our third, as opposed to big endian, where this would be our first. So the little endian is important because this is what Qiskit uses. This gave me a hell of a time first working through the, having to remember, oh, wait a second, it's in little endian. So I need to, flip this over, read this the other way, reverse it, etc. So essentially, what we have is the general way of writing this is I'm not really sure if we need to know this, honestly, but let's say we have 7 possible states. You can generalize this in this form, right? So yeah, not something that's really important. I haven't seen anything specific about. So pretty much, let's just keep moving through here. This is not really vital. So I found this very interesting. So this is the problem with quantum computing as a whole. Right now, at least. I know there's been some new advances from Microsoft, etc. But quantum computing has an exploding scale with higher and higher qubits in terms of the amplitudes, right? The number of amplitudes that have to be maintained with higher numbers of qubits. So, higher number of qubits. Where's my gibberish? So if n is, it says here, so if n is 300, So we have to track 2 to the 300 amplitudes, which is, I'm not going to rewrite that, but is more than the number of atoms in the universe. So we don't have classical computers that can track that, and the ability to have quantum computers that can do that kind of stuff, that can track that number of amplitudes, is a long way away. So we can also rewrite, similar to what we did when we were first talking about this, we can say, all right, we've got a bunch of, we say we have 5 qubits all in state 0. We can rewrite that as state 0 tensor 5, which expands to, this guy here, with the 5 qubit multiplication, or conversely this, or this. This is something we discussed yesterday, but parameterizing this into polar form, Cartesian, but basically so that we can take a single qubit and we can actually plot it on the surface of the Bloch sphere. So with a single qubit, boom, we can take theta and we can take rho, and we can apply that and plot that on the Bloch sphere. So there is no Bloch sphere representation. For multi-qubit. Because we have we have multiple amplitudes. Where before, if you have one qubit, this is our Z, this is our Y, this is our X, right? We can come over here and we can plot, let's say this. And we know that in terms of, for example, measuring this in the Z basis, we can calculate an amplitude for this, right? We can use one of the methods that we've discussed, right, to unveil the amplitude. We could do various linear algebra things to determine what the amplitude is, and thus determine the probability. But when we bring in more, now we go from just having 2 amplitudes, right? So if let's say we're measuring in the Z basis, then being in state 0 or being in state 1, now we've got 4 different amplitudes for 0, 0, 1, 0, etc. And there's no way to represent that visually in this Bloch sphere representation. So unfortunately, I know I'm a visual learner. We move out of that into the pure matrice and other notations here. That's essentially what we're reliant on. So the tensor product also that we were just talking about works for bras. So 0, 0. That's equivalent to 0 or a squared, or state 0 squared, or bra 0 raised to the 2nd power, or pardon me, with this tensor product here, or 0, 0. There's a number of ways you can write it. We can take a look at these inner products. So 1, 0 and 1, 1. Right? Really straightforward. We know that this works right here by matching up qubits. So we've got here and here, and so the inner product of this is simply 1, 0. or 1 times 0, pardon me. No, not 0. 1, 1, 0, 1. Oh, which is 1 times 0, which is 0. Similarly here, we have plus, minus, inner product with 0 and 1. Match them up. Multiply them. Plus times 0 times minus times 1 gives us 0. Similarly for the 3-qubit example, inner product of 2 states, or of 2 qubits, or 3 qubits, states, inner product of 2 3-qubit states. There we go. 1 minus 0. Well, since we're automatically going to be multiplying by 0 at the end here, with 0 times 0, and that'll be there. We know this is going to equate to 0, but let's go ahead and just, so 1 times 1 plus times minus times 0, 0. Kronecker product. So this was something new to me in this class. So Kronecker product, and is super important for things as we go forward. So the Kronecker product is how we actually assess tensor products. So 0, 0. This is equivalent to the tensor product of state 0 and state 0. We know that state 0 in column vector form is 1, 0. And the Kronecker product is where we multiply each term of the first matrix by the entire second. So this is our first matrix, this is our second. We know that we wind up with a column vector of 1 times 1, 0, and 0 times 1, 0, which gives us a 4 by 1 column vector of 1, 0, 0, 0. So they show that for a bunch of different forms here. So this is an example of a 2-qubit system. We can assess this with 0 and 1. We can assess this with 1 and 0, with 1 and 1. But these all have the resulting 4 by 1 column vectors. Similarly, we can state that the amplitudes, let's say we have a 2-qubit system with, so the superposition will have 4 positions, and we'll have our amplitudes C0, C1, C2, and C sub 3. We can this is just generalizing, right? So we've got, with 3 qubits, we'll have 8 amplitudes. With n qubits, you'll have n minus 1. Or where with n qubits, you'll have n minus 1, where n equals 2 to the nth. So let's say n is 5. That means n will be 2 to the 5th. That means we will have a grand total of 32 amplitudes to track. So similarly, with we saw it with kets, right? We saw, Jesus Christ. We saw it with kets here. That's with kets. With bras, it works the same way. So the Kronecker product of two bras, for example, is still just the tensor product of those 2 bras. So, for example, for these two zeros, the bra is simply the conjugate transpose. So we have 1, 0, that'll turn into a row vector, which is 1, 0. Similar here, a row vector, which is 1, 0. And now we just simply follow the same rules. So first, second, we will multiply every element of the first by the entire, all elements of the second. So we wind up with 1 times 1, 0, and 0 times 1, 0. So 1, 0, 0, 0. Perfect. We could do verification here. Let's do it. Let's do 4.5. Just to work the kinks out, right? Make sure we're good to go. So 1, 1, 0. We want to verify that this is equivalent to this 8, which is 0, 0, 0, 0, 0, 0, 1, 0. So we'll take the tensor product. We'll go from right to left. So 1, 0, 0, 1. So the right, or pardon me, the first one with the second one. So this equates to 0 times 1, 0, 1 times 1, 0. What are you doing here? I need new software. Okay. It's interesting. So the hand that pans around is selected. But whenever I click, it turns into the pen. Okay. You love to see it. Let's just, let's rewrite that up here. And which gives us 0 times 1, 0 times 1, 0, and gives us 0, 0, 1, 0. Now we'll take this whole thing and multiply it by 0, 1, by our state 1 here. So 0, 0. I'll do this formally so we can follow all the steps, right? So 0 times 0, 0, 1, 0. 1 times 0, 0, 1, 0. And we wind up with final form there. 0, 0, 0, 0, 0, 0, 1, 0. And that does match. So when we are, that also gives us insight to when we are assessing a multi-qubit state, like this is equivalent to this. We start with from the right. We start with our first qubit, and we move to the left in the order of operations. All right. Now this one's an interesting one here. Let's okay, new slide. Jesus. I don't know if this is a Microsoft whiteboard problem or a XP pen problem, but all right. So let's take a look at 4.5 because this one's interesting. So we have psi, which is a superposition of 2 qubits, but 0, 1 is missing, right? So we have 1/2 0, 0 plus I over square root of 2, 0 plus square root of 3 plus I over 4, 1, 1. Actually, what time is it? 2-minute break, guys. Gotta send the wife off to the night shift. I will be right back. All right, sorry about that, guys. For clarification, I'm not sending her anywhere. She's going to work of her own volition. So the 4.5. So we've got psi in this superposition, which is a 2-qubit state. And we know that the amplitude for 0, 1 is absent, right? It's 0. So whatever was done to these 2 qubits to get them into this superposition with each other resulted in this being 0. So just not important, just something I like to point out there. So what is this as a column vector? So we can we see here that these are tensor products. They're Kronecker products, and we know that 0, 0 is equivalent to 1, 0. The column vector is 1, 0 multiplied by column vector 1, 0, which gives us 1, 0, 0, 0 for our Kronecker product, plus I over square root of 2 for the resulting column vector for 1 and 0, which gives us, let's see, 0, 0, 1, 0, and then plus square root of 3 plus I over 4 times this, which is 0, 1, 0, 1, 0, 0, 0, 1. Yeah, perfect. So to write this as a column vector, we just marry everything together, right? So we've got 1/2 plus I over square root of 2 plus square root of 3 plus I over 4, which gives us, and then we add our column vectors together, which gives us 1, 0, 1, 1. We could, get these into the correct, into matching denominators and combine. I'm not sure if that's necessary. Let me see if the textbook has that going on. 4.5. No, actually, that is not what they have. They have they simply just distribute these into the vector before they add them. So 1/2, 1. So we wind up with 1/2, 0, I over square root of 2, and then square root of 3 plus I over 4. There we go. All right. All right, so this one's an interesting one because this brings in that completeness relation we were talking about, when we can show that the various combos here with our outer products added together are an identity matrix, which is cool conceptually, but tell you what, we'll go to 6:30 on chapter 4, and then we'll stop and stop recording, and then we'll go exclusively to the knowledge checks. We'll work through those. So, measurement. Actually, real quick, I apologize. Let me just see where we're at in this. So we're on 144. This is a monster chapter. Quantum adders. 44. I think this is like it's like 230. Okay. So we still got a good chunk of chapter 4 left, but that could be a whole day tomorrow. And then chapter 5 is software based, so we can just skip over that one. Okay, 144. All right, measurement of individual qubits. We've done a lot of that over the past few weeks, that's for sure. So similar to when we measure a single qubit state, we have some superposition of 0 and 1. And when we measure, it's going to collapse to either of these with a probability given by the norm square of its amplitude, right? So let's say square root of 3 over 2 and 1 over 2 will collapse to 0 with probability 3/4 and collapse to 1 with probability 1/4. When we have multiple qubits, and we measure one of them, let's say let's just follow the example here. So let's say we have qubit 1 and qubit 2. So when we measure qubit 1, it'll collapse to either 0 or 1 with some probability. Measure the left qubit. I'm trying to figure out where is this example they're talking. Oh, I see. Okay. So they're using this example. Let me write that out. 1 over square root of 2, 0, 0, plus 1 over 2, 0, 1, plus square root of 3 over 4, 1, 0, plus 1/4 1, 1. So pretty much, let's say we're going to measure the left cubit, right? We're going to measure this guy. So the probability of getting a 0 is the probability, the probability of getting a 0, and when we measure the left cubit, is the norm squares of these two guys added together. Because this is obviously this is the positions where the left cubit is 0. So it's norm square of 1 over square root of 2, norm square of 1 over 2, which equals 1/2 plus 1/4, which equals 3/4. And so we know, just, we could literally prove it by doing another norm square, but if we know that the probability of getting left cubit 0 is 3/4, well, we know it has a sum to 1, so probability left cubit in 1 is therefore 1/4. So when we measure, then these are going to collapse to 0, 0 or 0, 1. Now, one thing that we noticed, so the state will collapse to these guys, right? Now, as we talked about with normalization, these have to equal 1. So what we can find a normalization constant, A, that normalizes these so that when we take the norm squares, they'll sum to 1. So when we measure 0 with probability 3/4, the state collapses to this guy. Once we find our normalization constant, our new amplitudes, so A is equivalent to 2 over square root of 3. Or, 2 over square root of 3, so we get square root of 2 over 3, 0, 0, plus 1 over square root of 3, 0, 1. And similarly with 1, right? Collapses to, with probably 1/4 to these other guys here. And then we find that there's another normalization constant that normalizes those amplitudes. You can do this to any number of qubits, right? So 3, 4, 5, etc. It all follows the same kind of principle. Okay, so let's, for example, let's take a look at, let's do 4.7 and 4.8 real quick. So we have this superposition, 0, 0. EI pi to the divided by 100, Jesus, over square root of 10 plus square root of 3 over square root of 10, state 1, 1. So what we measure in the z basis, the 0, 0, 0, so with those states, what are the possible outcomes? So, well, we know there are 4 possible outcomes. There's 0, 0 with amplitude I over square root of 10. We take the norm square of that, and we get 1 over 10. Similarly, for 0 over 1, we get the norm square of 1 minus 2i over square root of 10. We'll multiply, that means we're going to multiply this by its complex conjugate. Or rather, this is gone now. It's just 10. Which equates to minus 2, 5 over 10, which equals 1/2. Similarly for this guy, wait, I didn't even put the state there, sorry. 1, 0. So for 1, 0, again, we'll take the norm square of that guy. So we know that when we take the complex conjugate of this and multiply it by itself, we get e to the 0. So it's e to the 0, which equals 1. And that's going to be over square root of 10 squared, so 1/10. And then our final one here, square root of 3 over square root of 10. Norm square for that, easy peasy. That equals 3/10. So when we measure this superposition, when we measure these two qubits, we'll wind up in state 0, 0 with probability 1/10, state 0, 1 with probability 1/2, 1, 0 with probability 1/10, and then 1, 1 with probability 3/10. Normalizing with 4.8, so we've got, again, another superposition of two qubits. Zero minus 1, 1. So we need to find a normalization constant which will normalize our amplitudes. So basically, let's see if I can exactly remember how to do this from yesterday. Pretty much we need to figure out, it's going to take us to 1. Let me put that here. There you go. All right, perfect. So the exact process for finding A is this. So basically we're going to distribute A through, and then these amplitudes multiplied by A, so we get 1/2 A. We get AI, square root of 2A, negative A. These multiplied by their complex conjugates added up will equal 1, right? So 1/2 A, well, times 1/2 A plus AI times A negative I let's write this like this, negative I times A plus A square root of 2 squared plus minus A squared, and all this has to equal 1. So we can distribute everything here. So 1/4 A squared. Minus I squared is just 1. So we get A squared there. We get A squared, or 2A squared. And we get A squared here. So getting everything distributed here, we wind up with 4A squared plus 1/4 A squared equals 1. We can put this in terms of, we put 17/4 A squared equals 1. I believe that's correct. Yes. get this isolated. So a squared equals 4/17. And we'll take the square root to finally find a. So a is equal to 2 square root of 17. And let's verify that in the textbook. This is 4.8. Yes, 2 over square root of 17. And once we apply this normalization constant to our superposition, multiplying it by all the various amplitudes, the amplitudes will be normalized. Okay, yes, about 3 minutes. So, similarly, this is pretty straightforward to put into in a minute here. So sequential single qubit. Well, we already know what happens when we measure. We've got this 2-qubit system. We measure, let's say, let's say it's in the Z basis, so 0 and 1. We have those 4 different combinations with various amplitudes. Well, when we measure it, it collapses to these guys, so we measure our first one, and it collapses to either this superposition with some kind of normalizing constant or to this superposition with another normalizing constant to make sure that our amplitudes are good to go. And then when we measure our second, let's fill in these amplitudes here like they do, C2 and C3. So it's the norm square of C0 and C1 for the first qubit to collapse to 0. First to 0. The C2 and C3 for the first one to collapse to 1. And then if we're going to measure the probability of the second qubit, right after that, we're gonna measure the next one. So if we measure the second qubit after we measure the first one, then now we have the probabilities of, let's say our first state was 0, and now we're going to measure 0. So the probability that our second qubit will be 0 is C of 0 squared, and the probability of 0, 1 is C of 1 squared, and so forth. So we break it down into we measure, it collapses, and then we measure again, and it'll collapse to one of these final states in our superposition when we measure the second qubit. Okay, that's going to end Wong coverage. Chapter 4, as I said, is freaking massive. It's aside from chapter 7, it's the bulk of the book. So I'm going to stop here. Tomorrow we'll lead off with entanglement, but for right now I'm going to stop recording and get us set up to look at the knowledge checks and the problem set. Even though the first problem set has some stuff that comes a little bit later, we might have to revisit that tomorrow in the second half. But there's enough in the first problem set that just is kind of really focused on the simpler stuff that we looked at, that we can mess around with that. So stop recording.